Hello, this is lecture number 10 in the Philosophy 201 Introduction to Logic course. And we're going to get a couple things done in this session. Although in one sense, there will be no concept introduced today that you don't already know. So in fact, between now and the midterm exam, you won't learn any new proof rules. However, what you will learn how to do is to stack new proofs on top of old proofs, so to speak. So you'll learn how to solve harder problems by building up intermediate steps. Okay, so that will be our main focus today. I'll call that harder proofs. And this covers some ground that's discussed in chapter 4. And also as side points, I'm going to mention a new logical connective, this double arrow, which is called biconditional. And along the way, also introduce two types of sentences, tautologies, and contingencies. So those will all be things I hit upon in the discussion today. So let me just start by telling you about the concept that we'll employ to solve harder proofs. So if you look at this picture here, this slide, the blue box, basic rules, these are the rules that we've learned. So these are the rules that are stated in the book, rules such as and introduction, and elimination, and then the list goes on. So all the rules that you have permission to write on the far column in a proof. Now, the fact is there are some things you can prove that would be useful as rules, but we don't need them as rules because you can prove them from the basic rules. So we could call those derived rules. So here's one example of a derived rule is from not phi or psi, the following sequence is provable, not phi and not psi, and oops, that's a mistake, not psi. This is called De Morgan's rule. This is one of De Morgan's rules. And so in fact, in the middle of a proof, if you had not phi or psi in the main column of a proof, you could just interpolate your old proof whose last line was not phi and not psi. So now I'm going to simplify your life by saying what you can do when you have permission to use derived rules is you can just say that. You can say De Morgan's and make that one step. So I'll do that first. I'll just show you an example of that really quickly on the next slide, and then we'll work together a pretty hard problem using this technique. Okay, so let's see how De Morgan's would work. Okay, so suppose that I'm going to prove, suppose I have not P or Q. Now, the proof of De Morgan's shows you that if you wrote it out in full, it would take you some number of lines, and then down here at line N, you'd have not P and not Q. Who knows what you'd have as your justification, but what we do know is it would depend just on one, because it means this sentence, not P and not Q, follows just from line 1. Okay, so what one can do to make their life easier when you're proving more difficult things is you could contract this whole thing. So I'll just literally do it in front of your eyes. So I'm going to cut this bottom line. I'm going to move it up right below line 1. I'm going to change it into line 2. This is now line 2. And this follows from line 1 by De Morgan's. So this is not a new rule. What you're seeing is what you could have done in, say, 13 steps before. If you remember that you could do it in 13 steps, you can do it in one step and say, remember, I could do it in 13 steps. Okay, so that's the most basic form of using a complicated rule that's described. So that in chapter 4, you'll see the name cut. Now, cut is just a fancy technical term for, hey, if I have a longer proof, I can compress the first and last lines and stick them in to another proof. So this is an example, what I've just given here, an example of using cut. So I just did De Morgan's in one line. Now, the truth is cut, you can also do it schematically. And what I mean by that is, suppose that you prove De Morgan's with not P or Q, so P and Q. The truth is that didn't depend on the identity of P, the letter P, and the identity of the letter Q. It just depended on the form. And so in fact, going back into this proof, the truth is anytime you had something of the form not phi or psi, you could prove not phi and not psi from that. So that's De Morgan's as a derived rule schematically. No matter what phi and psi are, they could themselves be complicated bits, but as long as you have the following form, that's a permitted step. Okay, now the key here in this case is that the dependency number, when you do De Morgan's, the dependency number of line, the final line, is just on line 1. Okay, so that's saying all you need is line 1 in order to do De Morgan's in this case. Okay, this is easily, as with so many other things in logic, it's easier to internalize it by doing it than by hearing me say it. So what I'll do next, instead of continuing to repeat what you can do with cut, is I'm just going to work through now an example of a proof. Okay, and this will also give me a chance, as I said at the beginning, to introduce a new symbol and to introduce a notion of tautology and the notion of a contingency. So the new symbol here is going to be this. So here we have phi, some sentence, this double arrow, psi. Okay, this is called the biconditional, and the reason it's called biconditional is because in truth, we'll just take it to be an abbreviation. So I'll write a sort of fake looking equal sign here. This is just an abbreviation for if phi, then psi, and if psi, then phi. And so it really means if and only if. Phi, if and only if psi. Okay, the other thing to look at really quickly is what is the truth table for this? And so I'll just write that out here to the side. So this biconditional has the following truth values. So once again, there's 4 total possibilities. The rule for this one is easy to remember. Phi, if and only if psi, is true whenever phi and psi have the same value. Otherwise, it's false. Okay, so in this case, it's true on line 1 and line 4, because that's when they have the same values, when they're both true or they're both false. And it's false on line 2 and line 3. So that's the truth table for biconditional. Okay. So we don't need any new proof rules for biconditional because the way you get a biconditional is just by getting the 2 conditionals. And then you can say, as an abbreviation, on the next line, I'll introduce a biconditional. Vice versa, if you have a biconditional on a line, you may take it apart into the 2 conditionals conjoined. So you could call that a rule if you want, but really it's just saying replace the biconditional with its definition. Its definition is 2 conditionals conjoined. Okay, good. Now, 2 more concepts, and then we're going to get going on that more difficult proof. Okay, the first concept is the notion of a tautology. A tautology is a sentence whose truth table, the main row under the main connective of that sentence, is always true. So always 1. So 1, 1, 1, 1, 1, 1, 1, a tautology. So in other words, it's always true, or 1, every line of its truth table. Okay, here's a quick example. The sentence P or not P. If you write its truth table, which has 2 lines because there's just one atomic sentence, so P can either be true or false, but actually in both cases, this is true because in the first case where P is true, that's enough to make the or true. In the second case where not P is true, not P is true, let me erase that because it's confusing looking. So not P, P is false, so not P is true. So the or is always true in this case. So if we write in, this is the main connective, the main column of the main connective, it's always true. And here's the important fact. If phi is a tautology, actually, let me write this more explicitly as a biconditional. Phi is a tautology if and only if the sequent, which has phi on the last line and no dependencies, is provable. Okay, so you know now, there's this fact tells you if something is always true in its truth table, it is provable. There is a proof of it, and vice versa. It is, if it's provable, there's always one under its truth table. Okay, why is that the case? We're not ready to reveal to you the magic that makes that the case, but it's a wonderful thing where you can compare truth tables and proofs, and you know they'll align exactly. In this case, something's provable, its truth table is always 1 under the main column. That's a tautology. A contingency is not quite the opposite of a tautology. A contingency is something that is sometimes true and sometimes false. So I'll write that down on the next page. A sentence is a contingency. Phi is a contingency means phi is sometimes true 1 and sometimes false. Zero. Okay, now I recommend to you at this moment, I'm going to ask you a question, and I recommend that you pause the video and you sit and think for a few minutes until you feel that you know the answer to this question. If a sentence is a contingency, do you know whether it can be proven or not? You should be able to answer this question from what we just said about tautologies. Okay, so that's the question. I'll write it down explicitly. Question. Can a contingency be proven? Okay. Now, let's continue. The answer to that question is no. A contingency cannot be proven. There's no possible way to prove it. Why? Because it's a contingency, and so therefore not a tautology. It's sometimes false, so it's not a tautology, but only tautologies are the things that can be proven by themselves with no dependencies. Okay, so in particular, for example, the sentence P, that's a contingency because it can be true or can be false, so P cannot be proven. Okay, another quick example, let's look at the biconditional P if and only if Q. P if and only if Q can be false because P and Q are assumed to be independent. And so if P is true and Q is false, the biconditional is false. If P is false and Q is true, the biconditional is false. So that cannot be proven. Okay. Now, one last question in terms of what can or can't be proven. Consider the following, at first, somewhat funny looking sentence. P if and only if Q, or Q if and only if R, or P if and only if R. question, can that be proven or not? Can this be proven? Okay, again, I recommend that you now pause the video for a couple minutes, and as long as it takes you to answer that question. So think about, can that sentence that I just wrote down, can it be proven or not? Okay, so let's continue now. This sentence that I just wrote down, I claim, I'm going to argue now that it can be proven, that this sentence can be proven. How do I know? So I'm going to give you a somewhat quick argument about truth tables. My claim is that the main column under this sentence in its truth table is always 1, this sentence. Okay, now I took a little liberty in the way I wrote the sentence, those of you who are a little bit nitpicky now about logic, which I encourage, I hope that some of you have become nitpicky. The sentence I just wrote down, the symbols I just wrote down are not really a sentence, right? Because you can't put you can't put 2 ors in, you have to group things with parentheses. And so in truth, I need to choose whether to group the first 2 biconditionals together in parenthesis or the second 2. That's technically correct. Okay. However, in this case, the final column is going to be the same either way, because or it turns out provably is associative. So it actually, what you end up getting at the end, it won't depend on the order in which you compute them. And so in truth, for an or to be true, for 2 ors, so if you have X or Y or Z, for that whole thing, the disjunction X or Y or Z to be true, it's enough for one of the 3 to be true. If one of those 3, X, Y, or Z is true, the whole thing, X or Y or Z is true, no matter where you put the parentheses, whether you put them around X or Y or around Y or Z. Okay, now I'm going to argue very quickly that this triple disjunction, one of the 3 will always be true. You don't know which, but one of the 3 always will be true. Okay, despite the fact that we know that each of the individual disjuncts, we just saw each of the individual disjuncts can be false. So none of the individual disjuncts here can be proven. However, consider the following argument. Okay, suppose that the first disjunct is not true. Okay, so in other words, P and Q have different values. There's only 2 values, 1 and 0. Okay, so if P and Q have different values, if the first thing is false, P and Q have different values. Suppose now the second disjunct is also false. So Q and R then have different values. But there are 3 sentences, P, Q, and R. If P has a different value from Q and Q has a different value from R, then P and R have the same value, truth value. They're either both true or both false. So therefore, the third disjunct is true. So I just argued that if the first 2 disjuncts are false, the third will be true. Now you can see how that would cycle around. You can do it in any order. You can say if the second and third disjuncts are false, the first will be true. If the first and third disjuncts are false, the second will be true. So the fact is, no matter what, this overall sentence will always be true. It will always be 1, and therefore, as we promised, it's provable. Believe it or not, it's provable. Okay, the next thing I'm going to tell you is if you tried to prove this, just brute force using the basic rules, you have a very bad time. Okay, even if you love logic as much as I do, this won't be your favorite proof to work through. It will be a long slog. Okay, so what I'm going to do now is I'm going to use derived rules. Okay, so let me give you a little hint here. If you look in the back of the textbook, which the author very wisely prepared a list of useful valid argument forms. So these are things that you can prove using the basic rules and things that are very useful for proving other things. Okay, so what I'm going to do is I'm going to freely help myself to using any one of these and applying, thinking in terms of the rule in chapter 4, cut, but that just means I'm going to get to invoke any one of these derivations in this list. Okay, so you may want to have your book in front of you and look at these two pages. So it's on page 233 and page 234. And so I'm just going to use these as I sketch out for you how a proof of this thing would, the proof of the sentence we're looking at, how it would go. Okay, so my goal is prove this guy. Okay, so what I want to do here is I'm going to think of a strategy for how to prove this thing. I know that I'm not going to be able to prove any of those individual disjuncts because they're not tautologies. The big sentence is a tautology, the individual disjuncts are not. Okay, so I'm going to try a reductio ad absurdum strategy. So I'm going to go ahead and assume the negation of that whole big thing. So negation, and I'm going to use square brackets just to keep my head clear as I proceed here. So it's no different in principle from the rounded brackets. So this is my assumption for reductio ad absurdum. Okay. Now is when I'm going to allow myself to use something from that list of useful validities from the end of the book. I'm going to use De Morgan's now. Okay, so I'm on line 2. I'm going to go ahead and I'm going to push the negation sign in. So not P if and only if Q, and not, and then this whole second thing, Q if and only if R, or P if and only if R. Okay, so how do I do that? So what I do is De Morgan's is from one sentence, you get another sentence. What that means is, in this case, if I have that first sentence on one line, I can write the derived sentence on the next line. I just carry down the numbers and I write the name of the derived rule or the valid inference, in this case, De Morgan. So I'm just writing DM for short here. If you look in chapter 4 and you follow the letter of the law strictly, it would say write cut. But in truth, cut just means, hey, I know what I'm doing. I have permission to do this. So because in any case, notice what we have here in front of us is not technically a legitimate proof. It's a note that a technically legitimate proof could be built, okay, if we went back in and put in the steps of De Morgan's that we've done before. Okay, so now I'm going to break that thing up using and elimination. So let me be totally clear that that was back on that previous line, that was De Morgan's applied to line 1. Okay, so now I'm going to take apart this conjunction. So P if and only if Q. It's 2 and elimination. And then also that second negation, Q if and only if R, and P if and only if R. Okay, there's a typo in what I just wrote. That was an or. Okay, and so now I'm going to just do De Morgan's again. So now I'm going to put not Q if and only if R, and not P if and only if R. Okay, and that is from 4 De Morgan's. So now I'm doing De Morgan's again. Now let's take this apart using and elimination. So not Q if and only if R. That's from 5 and elimination. And not P if and only if R. So that's also 5 and elimination. Okay, so lines 3, 6, and 7 here are going to be the key lines for us. So we're going to see in a minute that those do contradict each other. So what we have here is it's not true that P if and only if Q, which really you can kind of read as it's saying P and Q don't have the same value. 6, not Q if and only if R, saying Q and R don't have the same value. 7 saying not P if and only if R, P and R don't have the same value. That's not consistent. There's only 2 truth values. Each sentence is either true or false. So those 3 are not consistent, but how do we actually draw that out in terms of actual proofs? And again, if you go and scan through the list of useful validities, what you'll find is one of those useful validities tells you that not a biconditional, so not, say, P if and only if Q, is equivalent to not P if and only if Q. Okay, so not outside the parentheses, not P if and only if Q is equivalent to not P just by itself is equivalent to just Q by itself. Okay, that's one thing we can do. And the other thing we can do is we'll use the fact that biconditionals are provably transitive. So if P is equivalent to not Q and not Q is equivalent to something, then P is equivalent to that third thing. Okay, so we're going to use those 2 maneuvers. So I'm going to start, and now it's going to get a little bit sketchy just because I'm going to run out of space here, and I just want to give you the idea of how this would proceed. Okay, so I'm going to go back first from line 3, and I'm going to write P if and only if not Q. So that's going to be 3. And now, what's the name of that thing? I'm just going to call it BC for biconditional. So it's biconditional negation, negated biconditional. Okay. Then from line 6, I'm actually going to do the negation in the other direction. So in this case, not Q if and only if R. So 6, negated biconditional. Okay, and then finally 10, looking back at line 7. Line 7, I have not P if and only if R. So that's the same as R if and only if not P. So that's 7 biconditional. Okay, now it should be even more clear that we have a contradiction because lines 8, 9, and 10, P if and only if not Q if and only if R, R if and only if not P. Okay, so I'll just, to be a little bit careful about this, I'm going to first put 8 and 9 together using transitivity of biconditional. Okay, so we're going to have P if and only if R. So that's 8 and 9. I'm just going to call this transitivity of biconditional. Okay, and then putting 10 and 11 together. Okay. Now, it's obvious in one sense. It's obvious that line 12 is a contradiction. Line 12, P if and only if not P, that can't be true. That's never true. Now, but it's not a contradiction in the sense of reductio ad absurdum. Reductio ad absurdum says you need something and its negation. Okay. So the next and last thing in this proof is to say, if I have P if and only if not P, I actually can prove from that P and not P. Okay. I'm not going to fill in the steps of that at the moment. I'm just going to tell you that as with the other things here, De Morgan's and the transitivity of biconditional, it's something that can be proven on its own. How would it be done? Well, for example, you could show that any biconditional, say X if and only if Y is equivalent to X and Y or not X and not Y. Okay, so in this case, P if and only if not P is equivalent to either P and not P, or not P and not P, which is equivalent to P. So in either case, you're going to get P and not P. Okay, so this last step, I'm going to leave as a little bit of a mystery. This step from 12 to 13. But I assure you that this is that from P if and only if not P, you can prove a contradiction. You can prove something and its negation. You can easily prove P and not P, but the fact is you could also prove X and not X. Any contradiction follows from that from line 12. Okay, so as you can see, even with allowing myself to use derived rules here, I have a 13-line proof. Imagine how horrible this would be if you couldn't use derived rules. So what if from lines, what if back at the start, going from line 1 to line 2, I had to write out a full proof of De Morgan's? That would have been at least something like 10 more lines. And then what if then when I used it again on line 5, again, another extra 10 lines. And what about then also these negated biconditionals? That's going to be many lines to prove that the negation of a biconditional is equivalent. So as we used here from going from line 3 to line 8, we used one step where actually if you wrote out in terms of basic rules, it would take something like at least 10 steps. The truth is this overall proof, I don't think it can be proven from basic rules in less than maybe 50 lines. Okay, it's really, really quite bad. So this is what derived rules will let you do. Now, the other last thing to say here is notice how we used intuitions from truth tables together with proof rules. So the fact is the reason we know it's provable, we look at this top line here, P if only if Q, or one of these other two biconditionals, the reason we know it should be provable is from truth table reasoning. So we know that P and Q and R, they only have two possible values. And so this thing is just always going to be true. So it must be provable. How you actually get down into the details and prove it is a much more difficult thing. Now, this is as complicated as it gets with propositional logic. In the next problem set, we'll give you a chance to do the same sort of thing. And the general advice here is become comfortable with the derived rules. How do you do that? Well, hopefully you've already done your homework diligently into this point. And then on top of that, look back in the back of the textbook at these useful validities and prove every one of them. Prove every one that you can, get familiar with using them, and then you'll be able to, in more complicated proofs, just bring those in. Okay, so that's it for today. And we'll move on to discussing a little more about truth tables in the next session.